be recording now. I'd like to welcome everyone to the next in a series of webinars from NCSA and the Delta Exceed system. We're happy that you joined us today and hope that you're having a good morning or afternoon, depending on where you're located. My name is Greg Bauer, and I am a Senior Technical Program Manager at NCSA. I've been at NCSA since around 2000. So I've been around a while, and from most of those, well, for a good number of those years recently, I've been working primarily on the Blue Waters supercomputing system, but I'm co-PI on the Delta system that you're probably more interested in. So before we begin, we need to do a few housekeeping items, and one of which is reviewing the code of conduct. When you register through the Exceed portal, you're asked to accept the code of conduct terms for participating in the webinar, and that's what's presented here. The event organizer here for today and for most of the series is Jay Alameda, who's my colleague at NCSA, and many of you know has been a long time member of the Exceed organization. And so if you have some issues with respect to how members of the presenter or members of the attendees are behaving or with respect to the materials, there's a mechanism for you to let Exceed know. You can contact any of the ombudsman persons listed below, or you can go to the URL below as well for the code of conduct. There's a form, anonymous form, which you can submit your concerns or complaints. Oops, sorry about that. The second that we'd like to review is a terminology statement that Exceed likes to have. Exceed is committed to providing training events that make it easy for everyone to participate in, and that applies a lot to how we talk about some of the technology and some of the infrastructure that we're working with, and not everyone is at the same level, so we like to be as inclusive as possible. And we'd also like to avoid any terminology that could be viewed as being offensive. So if you happen to encounter any of that in today's presentation, we ask that you do let us know. And listed below, there is a terminology task force email that you can send to with your concerns. And everyone does their best to make sure that we abide by kind of certain standards, and sometimes it does get a little difficult with excessive acronyms and terminology. But we hope that today's material is accessible by everyone or to everyone. All right, next would be upcoming webinars. So many of you who are Exceed part of the Exceed community, you should have got an email earlier this week about a general Exceed new user training opportunity that'll take place Friday, December 10th. And that's for people new to Exceed in general. So if you're a new user of Exceed resources or wish to be a new user of Exceed resources, please go to the Exceed portal and look for upcoming training opportunities if you did not receive that in an email. And many of you are wondering when Delta will be operational, and we are eagerly awaiting the arrival of the system soon. And at some point, after the vendor has had their time deploying the system, we'll hopefully get time on the system to make it functional for our general user community and have an early user or early science period on the system. And around that time, we will hopefully have a early user training event to coordinate with that availability. And at the moment, we're looking possibly very early February. We understand that there are substantial delays, but I think that's pretty uniform across the board that everyone's experiencing delays due to supply chain issues. All right. So also during today's webinar, if you do have questions, we would like you to post those in the chat. And from time to time, the presenters will have opportunities for us to go through the comments in the chat and answer those at opportune moments. And then if some of those questions are more detailed and require more in-depth discussion, those can be taken either at the end of today's webinar or can be taken offline and being done through email as well. All right, and without further ado, I'd like to introduce our speakers for today. So the topic for today's webinar is an introduction to AMD's EPYC architecture and programming environment on Delta. And our speakers are from AMD. We have Dr. Alan Minga, who's a field applications engineer, otherwise with an HPC specialist, and his colleague Boris Conwie, who's also a field applications engineer and associated with one of AMD's Center of Excellence. So Alan, who I have not met before until starting working on the Delta project, has been working at AMD for quite a while and has 30 years of experience in high performance computing. He has used his engineering background to architect high performance computing solutions, including providing high performance CFD systems to Formula One customers. So I think we saw many years ago AMD highlighting their impact on modeling for the Formula One environment. Before joining AMD, Alan worked for NEC, I believe, and for Cray for many years. And Alan has a PhD in aerospace engineering from the University of Alabama. So he'll start things off. And then Boris will take over. Boris is known formally as David, but he goes by Boris. And maybe he can discuss that. And Boris joined AMD in 2003, which is pre-Opteron days, for those of you who go back a ways. Boris is a member, as I said, of the AMD HPC Center of Excellence, which is based near Boston at the Boston Design Center. And he likes to note that pre-COVID, he used to travel all over the world, talking with past and future AMD HPC customers. And I know many of us are starting to travel more. And so hopefully that kind of interaction will resume, hopefully. And before joining AMD, Boris worked at several startup companies. And Boris has a master's in computer science from Cambridge University. So Boris, if you're ready to take over sharing, and Alan, if you're ready to start presenting.
The other thing you need to know about Boris is once you drop the quarter in the jukebox, you got to listen to the whole song.
All right, very good.
Yeah, so I wasn't too clear. Shall I start off and then let's just get the timing squared away at the beginning? How long do we actually have for the whole thing? Is it?
We can go all the way up until 2 o'clock. That's what we're scheduled for. And if people can hang on after that, that's fine. So if you guys want to split the 50 minutes, however you want to, that's fine.
Sure. Okay, let me, oh, hold on. It's now not advancing, dang. Very good. Okay, now it's advancing, good. Okay, so let me just, in fact, I've got a bunch of slides, mostly about the processor, and then we could probably take questions and then flip over. Alan has some more slides really talking about the compiler environments and sort of best practices and things that we've learned along the way. So I guess we're gonna flip it around from the original schedule where I'll talk first and then Alan could talk first. But we probably should take questions as we go because people might have questions during the chat window. Okay, so can you let me just check you can hear me? Get feedback.
Yep, very good.
Okay, good. Yeah, I didn't want to talk for a while. So basically, the Zen architecture, we've been on this journey now for a while where we've moved off of monolithic dies. The first Zen processor, we had a multi-chip module with the 4 core compute dies in the socket. And then on the Rome processor, the previous generation, we moved over to having this arrangement where we have a centralized IO die and a chiplet with the CPU dies around the outside. So this is kind of the journey we've been on. Initially, we kind of did this because frankly, we didn't have enough money to build lots of different monolithic die for all the different SKU flavors we'd like to build. So, and also the CPU process is actually fairly expensive. So it was a good idea to have these smaller die for the CPU process, which then gives us better yields as well. So there's kind of a lot of advantages, but quite a lot of this stuff was based on expedience, not necessarily massive architectural insights. So this is the sort of journey we've been on. We started off, we've got HBM on the GPUs back in 2015. We moved to multi-chip modules with Zen. We're now sort of all in chiplets. And as we move forward, we're going to have more and more stacking. So we've got a processor coming on with an L3 stacked. On the GPU side, we've got stacked memory. There's a lot of advantages as we move forward to having these things stacked rather than just, I guess the sort of end of Moore's law is we can't keep shrinking these things. So we do have an aggressive roadmap for stacking the processor. So we'll deal with this architecture then has certain implications for the end users. So we'll deal with what those implications are as we go. So again, on the core side, we started off with the Zen 1 core. It's a x86 core at 12 nanometers. In Rome, we had Zen 2. The processor you're getting will have the Zen 3 core, which is actually 7 nanometers. And then next year, we'll be releasing Zen 4, which is actually 5 nanometers. And we're currently testing that stuff in the lab and beavering away on it. So here's a picture of the chiplet again. So one of the tricky things to actually put this plan into action is you do have to have this distributed, what we call the infinity fabric. You have to do distributed control of across the whole die and actually across both sockets. So you have to have a fabric, which is like a network, which does multiple things. So it has control infrastructure, it carries memory traffic, and it generously binds everything together. So it's not really it was a long process to get that defined, and then another quite a lot of work to get the various components to handle that across across all the different chips that go into the socket. Now, the other interesting thing is this: we can have a different process technology for the memory I/O die. So we can be one step behind the more expensive process, which the CPU is actually on. And we can then, what else can we do? We can then reuse the CPU die across different product lines. So in fact, the client probably uses a very similar technique, a very similar CPU die to the ones we use on the server processors. Okay, let me just dig a little bit into the Zen architecture, just to give you a flavor of what's under the hood, moving from Zen to Zen 2. So Zen 1 to Zen 2. So basically, on each of these iterations, we're also, as we have a newer process, we then tweak the CPU core so it becomes more performant. So the hardware guys they just love this stuff. So I said I would show you, but I really don't want to get too deep into the weeds with this stuff because it gets very, very involved. But it's worth knowing what's under there because it has implications for how, what speed things run at given the power that's used, and also worth having a kind of general idea of how the thing works. So here's a picture of the sort of microarchitecture of the Zen 3 core. So what we have a socket instructions, we have an instruction cache, we have a very chunky branch predictor. We cache actually the opcodes so that we don't have to repeatedly decode them. We then have a queue and we have a dispatch engine. So it's almost like we have two different processes under the hood. We have an integer side and then a floating point side. These have all manner of tricks to make the thing be able to gobble up horrible code and reorder instructions, do register renaming, wait on memory, schedule things correctly, and then drop into the address generation units or the integer into the arithmetics unit, so that you have these different pipes for the ALU and the address generation for putting results back to memory. On the floating point side, this processor, it's AVX2, so it's got a 256 two 256-bit wide multiply accumulates, so it does 16 DP, 64-bit flops per cycle. So one key thing is do not, if you have code using AVX 512, it's not gonna work on this. You don't want to do AVX 512. So in terms of what changed, let's have a quick look at this between Zen and Zen 2. Basically, Zen 3, it's a chunky, I call it a chunkier core. It's actually more instructions per cycle. It had lots of tweaks to the front end, enhancements. So the branch predictor does a lot of work to what can go wrong on these things. If you mispredict a branch, you'll get a bubble going down you get stalls in the execution pipeline, which is bad. So a lot of energy is spent predicting where branches happen and prefetching the instructions. In this case, we actually save some power by having an opcode cache, so we don't have to repeatedly decode the instructions. So this sort of runs through all these enhancements, faster recovery from mispredicts, better opcode features. I think we did actually tweak the cache, so we actually have this opcode cache now, rather than repeatedly decoding the instructions. So the high cache actually shrunk a little bit. And then on the execution side, it's a 4-way execution, six-wide micro-op dispatch, and 4-way scheduler thing for the integer side, and then various tweaks to the floating point, to the FMAC is quicker, and tweaks to the load store and the table sizes. So that result is, even though moving from Zen 2 to Zen 3, the process didn't significantly change. It was basically still at 7 nanometers. They got more instructions per cycle out of this thing. Okay, let's just move on. In Mike Clark's deck, he then digs into, in excruciating detail, each of the regions which have been tweaked, but I think we'll probably skip over that and get to the more user-focused stuff. Then we did have some instruction ISA improvements. So x86, sort of around the edges, there were little ISA instruction set architecture things which changed. So we'd add, we might add some things around AVX2, some of the so bit extraction instructions previously were microcoded, but now they're done in hardware. And then there was a bunch of stuff around security where we added more keys to the memory encryption, stuff like that. So here's a picture of the processor. Basic layout, each of these CCDs, which is we call that a core compute die, each of these has 8 cores and it shares a 32 meg L3. So the processor that you have, the 7763, is the top end processor. It's 280 watts, 64 cores. We can make other processors where we would either disable individual cores on the CCD, or we'd actually, at the lower end, we'll actually disable entire CCDs. But basically, all the SKU stack of the Milan architecture, they all share this basic architecture. They all still have the same IO die and stuff like that. Then the other thing that really changed on Milan is we now have the fabric is running in coupled mode with the 3200 memory. So we've sort of moved a little bit of the power to handling the fabric, which goes faster and has better latency. And then also we added the more security things. The cloud guys certainly like the security things, so we've added more keys to the memory encryption. So you can encrypt the memory on virtual machines, and you have a centralized root of trust security processor. But here's a picture. I think this is probably actually Lisa holding up a picture of the thing just to get an idea. It's about the size of a smallish cell phone. Okay, just to stress again, we then have the bigger L3 shared across all the cores. Previously on Rome, we partitioned the L3 so that you had these groups of cores which shared a 16 meg L3. This kind of gives benefits, possibly not such a huge benefit for HPC. Maybe it isn't a big benefit, but certainly a benefit where you've got cases where all of these guys are sharing L3. Okay, so basically we've got the IO die. The key thing is that the core compute die, they don't talk directly to each other. They all talk via the IO die. So we have the fabric. The core compute dies hang off the fabric, and then they talk to the IO die, which then talks both to the memory and to the PCI, and the GPUs or network cards, or across to the second socket. So this is a key thing to keep in mind, that your cores are they're not, although there's lots of cleverness so that they can do cache coherency between each other. They're not direct, they don't have direct connections. They're all the traffic is going through the IO die and the fabric. And we actually have a lot of bandwidth into the CCD. Each CCD has a lot of bandwidth. So typically the bottleneck is actually the memory. That's usually the bottleneck in any applications. An individual core can ingest probably a lot more bandwidth than via these GMI links than you could feed from the memory. This is just saying that we have coupled memory. So you have 3200 memory coupled with the fabric at 1600, which helps latency and it helps the stream memory bandwidth. So here's another picture of the IO die. And what this lets us do is we can actually configure this in the BIOS to have different numbers of NUMA regions. Typically, and I don't know, but probably your machine, you're probably going to set this up in what we call NPS 4 mode, where you have 4 NUMA regions per socket. And this is the fastest stream bandwidth and the lowest latency, because the core is talking to, if we chop this IO die up into quadrants, the core is connected to the top quadrant, would talk to the memory in their same quadrant. So you don't have a sort of extra overhead of traversing the IO die, which actually is not very large, but it's a little bit, it's a bit more latency and a little bit slower. You can also though configure this in what we call NPS 2 mode, where you could you basically slice the thing in two, or even in NPS 4 mode, where you would munge this thing into a big, into a big single NUMA region and interleave the memory across all of the CCDs. So I think for the most part, people in doing HPC stuff do NPS 4 because they want the maximum possible stream bandwidth, and they want they also have applications which typically are NUMA aware, so they can treat the thing as a NUMA, they combine the NUMA regions to their own local memory controllers. The other thing though to be aware is even if you have the NPS 4 mode, your NUMA regions are not now spanned by your L3. So your L3 doesn't span the entire NUMA region. So this is a kind of key difference between a traditional monolithic Intel processor. You'd have an L3 spanning your entire single socket NUMA region. So be aware of that. That's probably, I'd say, the biggest difference that you should be aware of. Okay, this is sort of borrowing from one of Alan's slides. So in some way, you could view the machine as a pool of these CCDs, even if you might want your MPI processes with OpenMP to do 8-way threading. Just treat these CCDs as little compute devices on this sort of global network mush of stuff. And in this case, though, you've got NUMA regions, you've got caches, you've basically got HPC is all about avoiding moving data. So you've got the latency to the L1, you've got latency to L2, which is dedicated. And then you have the shared resource, which would be the L3. You see the latencies are sort of stepping up here. Then your local NUMA region is fairly close. Your remote socket is bigger. You actually have quite a lot of nodes which are single socket, which would be good. So you wouldn't have the issues of remote socket access, but you would have the access of accessing GPUs. And then you've got the remote network traffic, which again, you see at each step, you've got a step up in the latency. And sort of the trick is to minimize these, you decompose your problem so you kind of keep everything as local as you possibly can. So one thing you typically wouldn't want to do, which if you just took a code and just ran it, you wouldn't want to typically have your OpenMP threads like spewing across a bunch of CCDs or a bunch of sockets. That's probably a bad idea. Just to mention the security features, you're probably not going to use this for HPC stuff, but the cloud guys certainly like this. So we have a secure processor to validate boot. We can encrypt the memory. So the memory controller has an encryption hardware encryption built into it. And then we can encrypt the memory of virtual machines, and we have other stuff to avoid malware attacks. So the cloud guys certainly like this, really because they sort of have a policy that any Tom, Dick, or Harry can jump on a node and share it with you, and they want to keep these virtual machines private to the user and have the user control the keys and encrypt their own memory and stuff. So for HPC, it's probably less impactful, but frankly, the memory encryption isn't massively expensive. It's not, you might take like a 1 or 2% hit, and it's not, it's certainly a viable thing to have turned on. This is just a picture of the security processor. It actually lives out on the IO die. So that's the root of trust. And there's an API to talk to this security processor. And it's a similar, I think it's a tiny ARM processor, which is similar to the security processor, which is in phones. So it's it's not something it's not a sort of security by obfuscation, that's the word. It's sort of security by hardware and hard keys and everything. So it's less at risk of hacking, I guess, than if you invented some funky scheme of your own. This is just to explain some of the security features that have been added as we go on between the processors. The main one in Zen 3 was actually adding more keys, I think, to the number of virtual machines we should support. Okay, so look at the SKU stack. The processor that you have is the top of the SKU stack. So it's this one, 7763, which is 280 watts default and 2.5 gigahertz base frequency with a 3 gigahertz boost frequency. In fact, you can configure these. We actually have a range of TDPs, so you can configure the processor to different TDPs. Over time, we started off, I think, at 225 watts up to 240 watts. Over time, the OEMs have kind of pushed us to do more. They like, oh, we can cool, 280 watts. We want 280 watts. So we've gradually crept up in terms of what the socket is probably getting a bit long in the tooth because it started off, it's socket compatible between Zen, Rome, and then Milan. But so the configurable TDP, we could actually, if you wanted to, you could dial it down. You wouldn't get as much boost, but generally for HPC, people crank it up to the max as best they can. This is just a thing about performance. The spec int rate. This thing is basically the fastest, I think, that's out there. Spec FP rate, it's probably the fastest processor out there too right now. But really because of the memory bandwidth. So, you know, it's lots of cores, lots of memory bandwidth, and it's sort of at the top of the game. So one way to think of this thing is that you actually have these shared resources. If you're thinking about, as a user, you're interested in certain things like what does a processor do? What does my code do? How fast does it run? So if you think about the issues of tuning a code, you do want to be aware that these resources are shared across these different cores. So one thing that's shared is the power. So we've got 280 watts. That has to feed the fabric. It has to feed all the cores, and it has to feed the IO die and the memory. So this is a shared resource. So if you run a code on just one core, it will boost more because it's got more power. If you run it on all the cores, or if you turn on all the floating point units to do a DGM or HPL or something, you've got more silicon turned on, and the boost frequency that you get would be less than the max possible frequency if you gave all this power to a single core. Likewise, you've got these memory channels, which are shared between the cores in the NUMA region. So you've got memory bandwidth is another shared resource. L3 is a shared resource because you've got those 8 cores. So I guess the message is if you have, if you have an application running on not all the cores, if it bottlenecks on a particular thing, don't feel obliged to run on every single core, because that's it'll probably get faster, but you're going to gradually, and depending on what the code is, you might hit other limits before you hit the limit of all the cores. So the 64 core, it's a kind of a jack of all trades, and it can emulate pretty much every other processor in the SKU stack. So then there's other things which are shared, like the TLBs. So these are doing address translation for 4K or 2 meg pages. And we have other things which are shared, which occasionally can cause an issue. So we have a page probe filter. So if we're doing random accesses, we have a protocol which lets the caches essentially talk to each other and check who's got which cache line. And there's a protocol for doing this, which involves sending out queries across the different CCDs. These get cached on a cache in the IO die. So this is a kind of shared resource as well, which is like all caches, they work, but at some point you can find a corner case which would bust the cache. Then to talk about the hardware, the frequency you get, this is just explaining a little bit because people sometimes don't quite understand what goes on here. So we have these P states. So basically the problem is we can run at different frequencies, these use, the higher frequencies obviously use more power. There's a frequency voltage response curve as we go up the stack. So in the old days, you would have a base frequency. So on your processor, the 2.45 would be the base frequency. And the OS then would move based on the power policy, would move between these P states, which are lower frequencies. These days, once you hit the top OS visible P state, the processor can boost. So it could boost all the way up to 3.5. Although it can also boost, depending on how many cores, it will boost up, above this, above the base frequency, but not all the way to the Fmax, which would typically be, if a few cores are active and all the power is going to those cores, and some of the cores are in the sleep state. So I think the takeaway is expect the thing, if you're running an integer code, it will boost above base. The default mode of your system is probably to have boost enabled. And if you're running a very floating point intensive code, it won't boost. If you have all the cores active, it won't boost above base, and it might even be a little bit below base. Although, frankly, the 280 watt part has got, it's the top bin part with lots of power. So it's actually not as constrained as some of the lower power 64 core parts. And just to explain this, here's a graphic that you can actually cap the boost. This is really just explaining that, okay, if you have more cores turned on, you're gonna, as you turn on more cores, you're likely not to see the maximum frequency, effective frequency. But if you're running an integer code, it will actually do really super well. And if you do something like, I don't know, kick off a big compile, the compiler's sort of integer based, you could see these cores cranking away. They're not necessarily fully loaded, but you'll see them boosting a lot. So the key thing is there's a hardware boost, which is independent of the OS policy. And this happens on a per core basis. So every core could be boosting on its own. It's not, it's not a kind of per CCD thing. This is just a video. So the client guys, they kind of do this boosting a lot. So, you could buy a client part, and depending on the motherboard, they'll give you, more power, more amps or more watts. So this video sort of explains the concept of what's going on. What the SMU is giving you is this boosting within this region. So the frequency voltage response, the current and the power is all tracked. And typically you would never hit the temperature because the system's designed with cooling and the SMU knows how much power to use. So temperature, it doesn't throttle based on hitting the temperature limit. Okay, I think I'll stop there and let's have questions, and then we could flip over maybe to Alan's stuff.
Great, thanks, Boris. Looks like we only really had one comment where someone was asking for what are the big differences between Rome and Milan, and I think you possibly addressed those.
I think I addressed those. Yeah, the main thing is the fabric and the shared L3, and the core is chunkier. So that's the main difference. So Milan is, the other thing is that Milan does use a little bit more power, but that's partly of choice because we sort of put the 7763 at the top of the power band, and then we put some other Milan parts sort of down low in the power band, and then there's kind of room where the Rome parts can coexist. So that was a kind of conscious choice.
Boris, don't forget the fabric clock runs faster on Milan.
Yeah, definitely. Yeah, that is definitely a key thing. The fabric clock runs at 1600, so it is coupled to the 3200 memory. So it's significantly better than Rome in terms of the bandwidth. And it also, there were some other kind of tweaks, which I guess they're sort of under the hood things.
I think Milan is capable of doing 3 loads and 2 stores per cycle.
Mm-hmm.
Whereas Rome is just 2 loads and 1 store.
Yeah.
Okay, great, thanks. I don't see any other questions, and on the interest of keeping things moving forward, why don't we switch over to Alan talking about the tools available in the programming environment.
Yeah.
Okay. Boris, go to the slide where I have app development best practices.
Yeah, I've got application developer best practices on the set. So I'll flip to the first one, and so basically the agenda is a spec, some comments on Intel compiler, the BIOS, advanced programming tools, and then hybrid and hardware locality. Yeah.
I mean, we're going to talk about it. I know most of y'all are probably used to coming from an Intel environment. And, the good news is we're all x86. We're all one big happy x86 compatible family. you know, we do not have an AVX 512 instruction set. I don't know that that's a big deal because, you know, typically AVX 512 doesn't give much of a performance boost, but you won't be able to run 512. You won't be able to run Skylake and Cascade Lake and Ice Lake instructions on an AMD processor. It'll just fail with an illegal instruction. But you know, notes on compilers: GNU 9.2 and later supports Zen 2 architecture. GNU 11 is Zen 3. LLVM 10 is Zen 2. 12 Zen 3. Intel, we'll come back to that a little bit later. But the other alternative here is AOCC, which is updated it's based on LLVM. Flip to the toolchain slide, Boris.
Sure. Okay, here's it. Yep.
Yep. So AOCC is based on the LLVM compiler. We take the released branch when a new processor is introduced. We add our changes, and then we release that out. It's free. It's publicly available. It can be downloaded from developer.amd.com. You could actually build the AOCC compiler with SPAC, and also the AOCC libraries. So that's kind of a neat feature. But and we're supporting SPAC recipes, optimal SPAC recipes for common HPC community codes. And that list is growing. Those are on developer.amd.com. So those are out there. On the Intel compiler, I think it's important to remember, you know, be sure to compile with March AVX Core 2, or March equals Core AVX 2 compiler flags. You know, don't use the definitely do not use the Xhost, because Xhost will embed, Xhost will take you down the wrong path for, it'll take you down a different path on AMD, something that's probably tuned for Pentium or something like that. Don't use let's see, don't use Xhost equals no, don't use X Core AVX2 either, because that embeds a runtime check that'll fail on AMD.
Yeah, I think the -X things tend to do a host ID, a processor vendor check, whereas the march things tend not to on that compiler.
Right. So let's say March AVX, March Core AVX2 is your options for AMD or for Intel compiler on AMD. For MKL, the story is kind of complicated. So there was a debug flag in MKL version 2019 that was depreciated in 2020, and in 2021 it looks like they have Zen kernels in MKL that generally perform better. But at the same time, our compiler team is attempting to, you know, if you note a discrepancy between MKL and AOCL on codes or kernels, if you can give us a test case, we're willing to go try to reproduce it and try to give you the best, make sure that AOCL is your best performance, right? So any questions on compilers and tools right now?
Yeah, Alan, we have two questions. One is from Jim Phillips, who was part of the AMD development team. He's asking, are the AOCC changes pushed back into the LLVM branch source?
They are, with a few exceptions, like I think one of the things that doesn't get pushed back is the non-temporal store.
Mm.
Although, Boris, have you played with the latest LLVM? Do you start
I
to
haven't,
see the...
Yeah, I haven't played with I've played with the most recent one and the one that can be built with Spark, but philosophically, yeah, the goal is to push these things back if the community would take them. There isn't really a goal to aggressively peel off our private, secret stuff and lock people into it. So the goal of the project is to peel off LLVM stuff, make sure we have a good compiler aligned with the processor silicon releases, because LLVM is on a kind of yearly release. So we want to make sure we're kind of in control of our own destiny on when the release cycle is, and then also have guys aggressively chase down issues that we see on our processes and in codes and stuff. So there is a goal to push things back. I don't know if some things the community, like non-temporal stuff, like for years the GNU compiler hasn't done that, which is kind of frustrating because it can't compile stream. But yeah, there isn't a policy to not, the policy is to push back anything I think that people will take.
All right, so we have a couple more questions that came up. Two of them we can kind of combine. One is looking for, is there a typical performance advantage over AOCC versus other compilers? And then the other question that's in the same line is, are there performance comparisons between Intel, AOCC, LLVM, GNU, et cetera, on Zen 3 for different common HPC applications? And then in the caveat is one person's reporting that they are seeing 7 times slower performance, I guess on Milan or maybe Rome with Intel compiler, with AOCC than with Intel or Cray compilers. So they're reporting a degraded performance, I guess.
Yes. Yeah.
So we'd definitely like to see a test case for that.
We'd certainly like to see it. So generally speaking, the Intel Fortran is probably ahead of the AOCC Flang compiler. But I'd say of the publicly available compilers, I'd say AOCC Flang is basically better. It's better than the GNU Fortran. In terms of C and C++ codes, Intel is usually bad. Well, I'd say bad. It's usually less performant than let me say it has less of an advantage than the Fortran than the GNU compiler, I guess, because GNU grows up with Linux, so GNU is pretty good and G++ is pretty good. If there are corner cases, and absolutely the OR is weird and horrible things that go wrong. Also, there are compilers do strange things, like they might be faster, but then they're kind of bending the rules on accuracy, which Intel is a bit naughty at sometimes. So yeah, if there are corner cases, we'd absolutely be interested. If you have something which runs dog awfully, there's probably something. It's either not using AVX2 or it's doing some weird stuff, which is the nature of the game, is that weird stuff happens and you have to figure out why, which is really why we got this whole compiler project, so we can go and chase these things down.
Right.
Okay, all right, when do we continue on?
Okay. So let's talk a little bit about multi-level parallelism. And, you know, I've been looking at some research papers about cache reuse and multi-level parallelism. And they seem to suggest, without calling out AMD specifically, that if, you know, in the past, if you've treated the memory space like an OpenMP domain, then there's some improvement if you have multiple L3 caches by treating the cache domain as a level, as the breakpoint or whatever you want to call it on your multi-level parallelism. And you know, I'm working to kind of put some test cases together to validate that, but it's not quite ready for prime time yet. What I suggest is for AMD kind of move the shared memory parallelism down to the L3 cache level. So if you're hybrid parallel, one MPI rank per L3, and then OpenMP threads below that, so that you're treating the L3 as kind of a breakpoint in the domain. And this is valid for Rome and Milan. I know there are some other Rome systems in the Exceed program, and y'all may use multiple systems. And you know, fortunately, there's an easy way to do this with a Linux utility called HWLOC, hardware locality tools, and that is built into most, I say most, MPI libraries these days. So basically, HWLOC is a database or info on the layout of the processor, and it makes it easy to do things like the multi-level parallelism that I talked about. Really, all you have to do what I'm talking about is add 2 lines to your MPI run, map by L3 cache, and bind to core. And that will get you to the point of it. If you look at what this is doing, it's actually spacing the MPI ranks. If you're running on Milan, it'll space it out every 8th core, because there are 8 cores per L3. And if you're running on Rome, it'll space it out every 4 cores. And the bind to is also important because, as Boris alluded to earlier, we have a distributed L3 cache. If you let Linux migrate the cores, you also have to migrate the L3 cache, or you get into some case where you have remote cache access from a core that's not on the same chiplet, which will hurt performance. So binding and map by utilities, and that'll probably get you, 95% of your best performance over doing some weird, custom rank kind of input file. Okay, so I'll stop there, ask for questions, but that's kind of concludes the short best practices.
Yeah, I think I've got, let me see, I think that's, yeah, okay. So I've got the, I've got to the MPI. So the key thing is these MPIs with HWLOC know about the L3 cache locality. So. Okay, questions.
Yeah, so we have a question, one that we'll probably try to address as well as once we have Delta on the floor and we're able to do some testing. But Ron Kaplan from PSI asks, how does one, and you address some of this, how does one set the proper MPI rank scheduling so that ranks are spread across the CCDs?
Yes.
Yeah, which we've had some experience too, and that can be a challenge. And then the other is, Delta, of course, will be also a GPU system. We'll have quad GPU nodes with one Milan processor, and then we'll have 8-way GPU nodes with dual socket Milan processors. And the question is how to best set ranks so that there is 1 or 2 GPUs per NUMA. And then is there a simple document that shows the right flags for using OpenMPI and MPICH? So hopefully we'll be able to address the latter with some documentation for Delta regarding some of that affinitization for OpenMPI and MPICH. But if you have any other comments that you want to say about rank placement.
Yeah, I don't know. Yeah, Alan, do you know about the GPU rank placement? I don't really have any experience on that.
Yeah, I'm gonna. This one's new to me. I'm gonna have to go off and research that one.
Yeah.
So.
And on Delta, just to be clear, on Delta, we'll have. I mean, NVIDIA is our primary GPU provider, but we will have one of the AMD MI150s, I think, or MI200 nodes. So we'll have a 8-way AMD GPU node as well. So we'll have a little bit of a mix.
Okay. Is that also the one with the affinity? Is that the Trento node?
No, I don't think so. No, I think
okay.
I think it's a box with 8 MI GPUs.
Yes.
And then it looks like you've got a bundle of nodes which are single socket with GPUs hanging off of the single socket, which in some ways is probably a less complicated scheme for because you don't have the socket hop to the remote network or anything. So that one might be easier to do the binding. Yeah, there might be a case even for doing, I don't know, the HPE guys probably have a lot more experience on this because they've done the machine at NERSC, which has all these GPUs as well, these AMD plus A100. There might be even, I'd say there might even be a case for doing MPS2 when you've got the GPUs rather than MPS4, but that's just pure speculation on my part, and they probably know much better what to do.
Sure. Yeah, we'll definitely talk to our colleagues there. And also to make things a little more complicated, we'll be doing a lot of node sharing. So not all the workloads will be able to use all the A100s on a node or even a whole A100. And so we'll be using MIG as well. And so making sure that we try to avoid contention for shared resources, especially in the NUMA level, will be a challenge, and we'll hopefully have Slurm. Hopefully, Slurm will
figure it out.
Help us out as much as possible.
Yeah. Well, one thing I know we have done is we've done the power stuff. So one of the things which uses power is the PCI and the clock talking to the GPUs and things can be controlled as well. So you can have you can downclock these PCI